Hey, I'm first to get started. Some announcements. We're still not quite far enough for me to release an assignment. So at this point, I can guarantee there will be nothing due next Wednesday, that the next assignment will be due the following Wednesday. So we're looking just about 2 weeks out for an assignment, which works well because there will be an exam next week. So I will be getting you a study guide by Friday so that you can start studying for the exam. The assignment that I do eventually give will probably be on the slightly larger side. So it will be worth getting started on that a bit, probably before the end of the exam, so you don't crunch yourself too much toward the end of that. But I plan to incorporate a lot of the material that we will be going over the next week or so of class before we start reviewing for this exam. I anticipate that the exam will cover a good bit of material from what we are covering over the next few days, but that will not involve any of the code implementations of a lot of this or the project that I eventually assign based off of it. So we'll be doing a lot of in-class work over the next few days as we go over quite a few graph-related traversal algorithms. And very similar to how ADL had an implementation related question on the last exam, you can anticipate there will be some graph traversal manipulations on the next one as well. So not a ton of time to do this over homework, but I anticipate that back and forth in class will hopefully clarify things enough to be able to do that portion of this unit on an exam. Questions or concerns about schedule? Any material before we dive back into, I'm halfway through the very last slide of this deck, which is very awkward, but we will very quickly be moving into graph traversal algorithms. Yeah.
No, it's probably
It'll be a week from Friday. It's not remotely on campus, so it's good that you're clarifying because the syllabus still says the exam was tomorrow, which obviously when we push the first exam back a week, I don't want to have 2 weeks between exams. There just wouldn't quite be enough material to throw on an exam in a way that I would be happy with. So yeah, exam will be a week from tomorrow.
And we have a third exam again.
Yeah, I'm anticipating that's probably going to be close to the last day of class, week 10. And that way there wouldn't be anything over finals week. There would just be a last exam on that last week.
Would that exam be cumulative or just?
There may be a couple of cumulative components in that I won't ask you a question that I should have asked you on an earlier exam, but kind of tying things all together. How does the study of algorithms relate to some of the material from the first exam, the second exam, so a larger picture incorporation of that material into the bigger picture. But yeah, I won't go and ask you to solve a recurrence like you would have expected to do on the first exam. Other questions? Last time we talked about both depth first search and breadth first search applied to graphs. So we've seen them in trees in data structures, but actually seeing them applied to graphs. How do we break ties? How do we explore nodes in an appropriate order? And at the very end of the last class, I started introducing the idea of iterative deepening as a way of taking the benefits of both breadth first search and depth first search and trying to come up with an algorithm that gives us both of those benefits. Depth first search had that linear memory that we really like. Breadth first search gave us the optimal answer in terms of the number of edges between the source and destination vertex. So we wanted to both use linear memory and get the best answer, and iterative deepening allows us to do that with a bit of a minimal trade-off, and that it can take up to twice as long. And I wanted to start today by explaining the twice as long, because it's a very similar idea to one that we've seen in this class a couple of times before, but I want to show another example of it. So let's refresh our idea of iterative deepening. We're going to use depth first search, but use a horizon of depth k. So we'll depth first search depth 1, then depth 2, then depth 3, then depth 4, and we wait to find a solution. When we find a solution, we know that it is the first solution that we've come to. If there was a shallower solution in the tree, we would have found it in a prior iteration of this iterative deepening. So when we do find a solution, we know it is the shallowest solution, which means that it's the fewest edges between that source and destination vertex. Anyone have any intuition as to why this would only take twice as long as breadth first search?
So, I'm sorry, I did not hear your question. Sorry about that.
This is going to take twice as long as breadth first search to iterative deepening up to.
Because at first search, you search every single node, every up where at. Which you're only doing the nodes that are actually.
Kind of. So let's draw out a bit of a tree here. We were assuming that we're going over a tree, and we're just going to assume it's a tree for the moment. When we see this in graph form, we'll see why this works as well. We'll draw this out to kind of this level. If we're iterative deepening to this level, we're going to explore this. Then we're going to explore everything. So this plus this. Then we're going to explore everything in the next level and shallower, everything in the next level and shallower. What do we notice, or what do we know about each of these as we? So if we just did a single depth first search, then we would be exploring 15 nodes. So what is the sum of everything before that and including this? How is that bounded?
Let's see. 11 plus 15, which is 26.
Yeah. So as this expands, as we do this layer by layer by layer by layer, we want to say that the total amount of work that we do to do iterative deepening, which is look at just this node, then depth first search these nodes, then depth first search the next level, depth first search up to the next level. We are summing each of these values, which is all of the nodes up to and including that level. If we were to draw this out in terms of powers of 2, this is 2 to the 1 minus 1, this is 2 squared minus 1, this is 2 to the 3rd minus 1, this is 2 to the 4th minus 1. So depth first search in this case is going to give us 2 to the 4th minus 1 total nodes to do. So DFS 2 to the 4th minus 1. I'm just going to say 2 to the n minus 1. And now breadth first search. Let's just do straight to iterative deepening. Iterative deepening search is going to be everything before that. 2 to the n minus 1 plus 2 to the n minus 1 minus 1 plus all the way down to 2 to the 1 minus 1. What can we say about the value of this sequence? Is it guaranteed to be less than 2 to the n minus 1? If we think about this in terms of binary numbers, 2 to the n minus 1 is just a bunch of 1s. 2 to the n minus 1 is those same number of 1s without 1. Imagine this sum compared to the value of the next one of these with 1 extra 1. Might be another way you could visualize this just in terms of binary numbers or binary arithmetic. If you sum this, it's going to be less than that.
Okay.
You could fairly easily write a proof of that. You could easily use induction. But again, I always like showing kind of the intuition behind what would cause you to go down that route. So we're bounded at twice the time, basically. Does it make sense how we tie that all together?
Yeah.
And say that iterative deepening is just the equivalent of a bunch of prior depth first searches. So how can we compare the value of every depth first search that we have to do with the next one? And so we can't possibly reach twice as large because of that. So it's bounded by twice the time. So as this problem scales, we get the linear memory of depth first search, because as we do this, we're never storing more than the depth number of nodes. So it works well. We get the benefit of depth first search, we get the benefit of breadth first search. The trade-off is that it will take twice as long. But asymptotically, twice is a constant. As the size of this problem scales, it will always take twice as long. The twice does not scale at all. It never becomes 3 times as long or 2.1 times as long. It's always twice as long. So this is what I just talked about. Like breadth first search, you get the shortest path by number of edges, not by edge weight. Like depth first search, we get that linear memory. So this scales much more efficiently to large problems, at least in terms of its memory footprint. You would find that you eventually run out of memory if you're using just breadth first search on a reasonably deep tree. This allows you to explore a reasonably deep tree. Takes twice as long, but it'll actually complete. So yes, you repeat some work, but the repeat of work is capped by twice as much work. So as always in this class and in general with algorithms, there will be downsides, but you want to be able to quantify those downsides to be able to compare the trade-off of the increase in benefits to the increase in detriments. And very frequently you'll find that the benefits outweigh the detriments, which mean that you can apply to some other algorithm. Okay, we're going to dive into something that is much more applied.
Dijkstra's algorithm.
Who's seen Dijkstra's before? A lot of people. Okay, so this will be a review for about half the class, but we will go into hopefully more detail than where you've seen Dijkstra's before. I'm guessing that was in networks. If those of you who have taken it in networks, who saw Dijkstra's somewhere other than networks?
I think I also recall, like with Tony and data structures, we just did discuss this a little bit.
Okay. Data structures?
Yeah.
Okay. Yeah, so this is a very, very, very important algorithm. It's worth knowing and going over. Even if you've seen it before, it's a good refresher just to do this. But in networks, you went over Dijkstra's. Did you do Bellman-Ford in networks?
Mm-hmm.
Yes.
We did.
Did you do Floyd-Warshall in networks?
That's not one we are familiar with, to my knowledge.
I remember Dijkstra film.
Okay.
Those are the main two for me too.
Yeah, so we'll do Dijkstra's and Bellman-Ford first, and then we'll go into Floyd-Warshall, because Floyd-Warshall is quite cool. It's the basic idea is it's an all pairs shortest path. Instead of finding a one source to every destination, you're going to find every source to every destination faster than repeating Dijkstra's for every initial vertex. So that's just a bit of a where we're going. Don't worry if that didn't make any sense whatsoever. We'll explain it in a lot more detail. That was just for the people who've seen it before. So now we've talked about searching graphs. We can search with depth first search, breadth first search, iterative deepening. There are many other advanced searches out there if you're interested in what those searches are. Assuming that we have Bojan back next year, I'll be offering AI fundamentals in the fall, and we will, a big part of that is how to search, both global search, local search. So if you're interested in graphs and analyzing graphs in a lot more detail, that's a good class to take. If Bojan is not back, that class will not be offered, which is unfortunate because I will have to cover this class. Common question in computer science. We have a source, we have a destination. What is the shortest path between them? That's a very important thing to be able to answer, you would expect, in order for a graph to be useful. This is how Google Maps tells you the best route to take between a source and a destination.
Yeah.
If we use breadth first search for this is something we could do. What would some issues with using breadth first search to find a shortest path be?
Well, maybe searching like every node for every path, and that would take a
Well,
lot of time.
It's gonna be very slow, yeah. So breadth first search's worst case runtime is exponential. So if your destination is very far away from your source, then you're going to be exploring an exponential number of paths based on that distance. So your time that it takes will scale with the distance from source to destination. The other issue is that it looks in every direction. And if you're looking in every direction, if the goal with Google Maps is to get from here to Spokane Arena, we're going to look 1 block west, but we're also going to start out looking 1 block east. Is it more or less likely that the shortest path is going to start in the direction of the vertex, the destination we're trying to get to? If we're trying to get to a destination that is west of here, we should probably explore a good bit west before we start looking east. See that we run into some roadblocks going west before we try to go around those roadblocks. That seems like something would be relatively intelligent to do. And then, yeah, it also doesn't account for weight. If we're using breadth first search, we would be looking for, in this case, the shortest number of edges. But yeah, if we're looking for edge weights, then we're not accounting for that either, which is another good downside. Issues with using depth first search for this?
Wouldn't guarantee the shortest.
Yeah, we wouldn't necessarily guarantee a shortest distance if we did this. We would have to luck into a shortest distance. It also just straight up may not terminate. If we are in an environment that has some kind of very, very, very long loop, when we reach the loop, we would recognize it, but you could start in a random direction, like to get to Spokane Arena, we're going to just start walking east. When is that road going to terminate? If you start on I-90, it terminates in Boston. We're looking for something that's a mile or two away, and we end up on the other side of the country.
That's fair.
And we wouldn't ever backtrack to start exploring. And if we did, we would backtrack 1 block from the end of I-90 in Boston and start exploring downtown Boston. Are you Spokane Arena? Are you Spokane Arena? Boston. So we would want some kind of algorithm that handles this in general. There's nothing that we've seen so far that would actually help us, at least in this class. Again, those of you who've seen Dijkstra's have seen the solution to this. But the most common search in graphs is the shortest path search. So this is the most frequently used algorithm on graphs. So we'll start with, we have a weighted graph. That means edges have weights to them. This is not something that breadth first search would have handled before, as pointed out. But one thing to note is that the actual shortest path may not actually be very close to the minimum path length by number of edges. It may be that we take 10 edges to find the shortest path, when there's a way directly to get there. It just is a very expensive edge. So breadth first search could find that minimum path length in B plus E. But breadth first search struggles with minimum path cost. Here's an example of a graph that really shows that. What is the order that breadth first search is going to explore this graph, assuming that the leftmost node is our source and the rightmost node is our destination?
Well, it's going to search like in every direction, so it's gonna try to find the least amount of edges, not the minimum amount of path.
Yeah, so we're going to explore maybe, we're gonna look at every node that is 1 away. This is 1 away, this is 1 away. Oh look, we found the destination. There's the path that we find. Is it the shortest path?
Yes,
by
but
number of edges, but not by edge weight.
no,
So if we wanted to answer the edge weight problem, this is breadth first search is only gonna work when the shortest edge weight is the least number of edges. So in any graph where that property is violated, breadth first search will not return the shortest path. It'll return a path. It'll return the shallowest path by edges, but not the best solution. One thing to also consider is in many domains, the edges for graphs could be negative. This throws wrenches in a lot of algorithms that you might want to run on graphs because of assumptions that those algorithms make. How do you know when you've revealed the answer, the destination of the path that you found is the best path? If you allow for negative edge weights, it could be possible that there is a longer, more edges solution to this that looks bad one step out, but eventually leads us back to, you can imagine on the prior graph, if we were looking at, let's just add something that there's an edge here with cost 300 and then an edge here with cost minus 400. Breadth first search would not find this path that actually reduces this. Anything that you might consider at this point is going to struggle with that idea where you have an initial edge that looks bad, and then you can recover from that getting to the destination with some path that ends up being net negative. So that kind of addition to a graph is going to cause problems. Negative weight cycles are especially interesting and bad because that means you can get from a vertex back to that vertex at a net negative, which means you can repeat that cycle an arbitrary number of times and approach negative infinity from just repeating that cycle over and over and over again. So how would an algorithm determine that there is a negative edge cycle? And because of that, the actual path from source to destination is minus infinity. That doesn't necessarily have a great real world case, but it should be something that doesn't break the algorithm that you write. So here's an example of a negative weight cycle. If the goal is to get from A to D, then it's going to really struggle to go from A to B and recognize that there's no reason to explore the B to C because that edge is more expensive than B directly to the destination. But you would have to explore that, allowing for negative edges, because it is possible that you can take that short-term hit to a longer-term benefit of finding that cycle. So shortest path from B to D. If we don't allow negative edge weights, then it's much easier. But as soon as we allow for negative edge weights, there's more that we have to go explore to be sure that the answer that we found is the correct answer. So that's why we need a different algorithm for whether our graph has negative edge weights or doesn't. So we are not going to allow negative edge weights for the moment, but we'll come back to the problem of if the graph has negative edge weights, how do we handle that? So we'll explore that soon. We'll start diving into Dijkstra's. So similarly to breadth first search, it looks very similar to it. It uses a very similar style and structure to breadth first search, but rather than looking at number of edges, it's now adapted to handle edge weights. Instead of a queue, we're going to use a heap. Underneath the hood, it's a priority queue, but underneath the hood of a priority queue is a heap. Who's not seen a heap before or knows what a heap is? Doesn't know what a heap is. Okay.
not to my knowledge, no, I haven't exactly looked too much into it in person, but I have heard tons of stuff about it.
Yeah, I was hoping that it's been covered in data structures. Maybe a show of hands who covered heaps in data structures.
I don't think it's super detailed, but.
Yeah, not really in detail, but operating systems have been pushing a lot harder on
Okay.
that one.
I can briefly introduce the idea of a heap just because it's an important structure to know as well. So there's one main structure, but two main different ways you can implement it as a max heap or a min heap. a max heap stores the maximum at the root, the min heap stores the minimum at the root, and other than that, the only guarantee that you get from a heap is that if it's a max heap, we'll start with a max heap. It's just a tree, it's a binary tree, just like everything else that we've talked about with regards to trees, but every parent is larger than both of its children. So that's the only thing that we need to worry about for the moment. The only heap quality, every parent is larger than both of its children. So you could have a legal heap that looks pretty ridiculous, like this. That's a fix for that.
Bigger than both its children.
This is a max heap, even though it looks nothing like you would expect, but it's perfectly legal. Every parent is larger than both of its children, even though there are larger values that are deeper in the tree, that does not matter. The reason we would use a heap is it's a kind of a sort, but in a way that we only ever know where the maximum is. We guarantee logarithmic time insertion and deletion into heaps, and we can very easily, in constant time, extract the maximum value. We always know where the maximum is, but nothing is strictly sorted in that capacity. Yeah. They actually don't. The insertion and deletion process ensures that the heap property is maintained. So if we wanted to do something, so the other thing about heaps is that they have to be complete trees, with the exception of the last level, where the completeness has to be as far left as possible. So this is not a valid heap, because this 20 would need to be as far left as it can be on this last level. So if we wanted to insert into this, we could decide that we want to insert 20, we're going to throw it in the place that it goes. But you'll end up basically bubbling that 20 upwards, swapping values until the heap property is resatisfied. So you would swap the 20 and the 1. And then since 20 is larger than 4, you would swap the 20 and the 4. And we are back to a legal heap again. And you would only need to make at most a logarithmic number of swaps as you swap it up the tree. If you want to delete something in a heap, you're going to end up swapping it with the last element, and then taking this last element and bubbling it down. And you would have at most a logarithmic number of bubbles down in order to recreate the heap property. So you get that nice logarithmic time insertion and removal, and if you needed to get the largest value, it's always at the root to the constant time access. So that's very useful in a lot of cases. So that is a heap. A priority queue is just a heap underneath the surface, because a priority queue will be able to return you it's like a queue is going to return you the element that's been in the structure the longest that has the highest priority. So you can imagine these now as people in line, and as soon as a very important person is in line, they'll just cut all the way to the front because they are the most important person in line. Given that there is no very important person will service the person who has been in the line the longest. So it's kind of like TSA pre-check is a priority queue. If there is the ability to handle someone in pre-check, we will take the person who has been in pre-check the longest. If there's nobody in pre-check, we'll take the person who's been in the general line the longest. So underneath the hood for this, we're using a priority queue. We're going to keep a set of visited nodes, and we're looking at the shortest path to that node from the initial vertex as we expand this frontier. Nodes that haven't been visited yet have a best distance that's been calculated so far, and by the time we visit each node, we will have guaranteed that we found the shortest path to that node. Once we go visit and expand that node, we know that that optimal path has been calculated, so we can return it. When we terminate, we know that we've calculated the shortest path from that initial vertex to every other vertex in the graph. We are answering the single source, single destination vertex problem, but it turns out that that problem is solvable in exactly the same amount of time as that single source to every destination in the graph. So even though we're only interested in one destination, we can calculate and store all of those values at the same time. So let's take a look at what that looks like. I'm going to use what I've called the frontier and call it the cloud for the moment, because it helps us to visualize exactly what a frontier is. We're expanding a cloud outwards among more and more nodes, kind of like a breadth first search. So the initial state, we're going to start with the starting node has cost 0. The best path from the starting vertex to itself is 0 because you don't need to traverse any edges to be at the destination that is the source. How far is it from this classroom to this classroom? Distance 0, we're already here. Every other node is initialized to infinity, or integer.max value, or just some very large number that the optimal path is going to be less than. At every step, we're going to pick the closest unknown vertex, unvisited vertex, another way to state that, and we're going to add it to the visited nodes, this cloud of vertices that we visited before. And as we update that, we're going to be looking at the edges that go through that and see if we can, through that node, provide a shorter path to every other vertex in the graph. If we can, we update those values. If not, we leave them as is. And then we solidify the shortest path to the vertex that we just visited. That one was guaranteed. So here's an example of what we've calculated so far. And if we're looking for the shortest path to this, then we can find, let's see, at this point, we've calculated the shortest paths to A, B, C, and D. We've solidified these values. But from here, we would look at the next shortest node. So we would be adding F to this next. We'll see exactly how that works with an example. As always, I like to give you some pseudocode. So for each vertex that's not the source, we set the cost to that node to be infinity. And whether it's been visited or known, we set that to false. We have not yet visited it yet. The source's cost should be 0, and the source is visited. So we go into a loop that just says, well, there are unvisited nodes in the graph. We're going to select the unvisited node that has the lowest cost in a table of calculated costs. At the beginning, we have a cost 0 and a bunch of cost infinities. The minimum of 0 and a bunch of infinities is going to be 0. So we're going to visit the source first. We're going to mark it as visited for each edge that is connected to that source. We're going to look at them and add weights. We're going to start with the vertex's cost to that node is going to start out, since we start with the initial node, it's 0 plus that edge cost. This just sorts the edges, the vertices that are neighbors of the source by the edge weights of how far they are away from that source vertex. Then we update the costs, the best path seen so far. We do that, and then we loop back around. So we'd be adding each one of these to the cloud of what we're going to see next, and we'll pick the minimum cost of all of those and expand that, look at its neighbors, and continue that process in a loop until we visited every node. Question?
No, I don't know. Sorry, just.
You're good.
stretching.
Good.
Thank you for asking.
Any other questions? I know that speaking about it in words or in pseudocode doesn't help as well as something that is visual. So what's coming next is the example. If there was a question I've missed, quite a while ago, sorry. It's a priority queue one that is sorted. The reason heaps exist is because you don't need to fully sort something. You just need to know there's a bit of a structure to that, in that the parent is larger than both of its children, but it's not fully sorted. It's kind of pseudo sorted to the extent to which it needs to be sorted to do what the heap needs to do. All right, so we're gonna run through an example. And I'm gonna run through this one. This is exactly the cloud that we just saw. But I'll run through one of these, and then there's one of these that we can use for practice, but it will probably take us the rest of the class to run through this one. So how do we initialize this? We are starting from A, and we want to get to, we can get to every other vertex, so it doesn't matter what our query is. So we could be trying to find the shortest path from A to G or A to H. It doesn't matter, it will take the same time to find the shortest path from A to every other node. So we're just going to set that up as a table. So this is whether we visited the vertex or not. This is the actual cost. And then we also need to store a backtrack of the node that we came from when we found that path. Because just like we've seen with other problems like this, if you don't store the path, you'll get the cost, but then you won't know how to get there. This is like saying, I'd like to get from, you open up Google Maps, you put in a source, you put in a destination, and it tells you, it'll take you 13 minutes to get there. Great. Where do I go to get that 13 minutes? You want the path as well as the time. It calculated the shortest path, it returned to you the time that it takes to get there, but you really need to know what turns to make in order to get to your destination. So we'll be storing the path as we go so that we have access to that. Okay. So we're going to start by initializing everything. You see that we filled out this initial cost. We are going to say that the source cost is 0, and the cost for everything else is going to be infinity. We're using question marks to represent that it is, we don't know what that cost is going to be, but its initial value is going to be, you can read those as very, very large numbers. So we start by expanding the source. We're going to visit the source, and that we've now visited. So visited from the source is yes. And we can see that the best way to get to B, C, and D at this point are the direct immediate connections from A. So we're going to look at each one of these neighbors, and we're going to update the costs for each of these to be the direct edge weight from our source to that node. For each of those, we are going to relate that the path that we did to get these costs came from node A. Questions on this first step? Does that make sense as to what we did and how that information got put into the table?
That makes sense.
So what should we visit next? We want to find the minimum cost of all costs in this table that are not yet visited. So ignore any row that has been visited, but we want to find the minimum in this cost list for every node that hasn't been visited. And that's C, with cost 1 at this point. So the next node that we're going to expand is C. And when we expand C, we're going to start looking at every outgoing edge. There's 1 pointing back to A. We've already visited A, so we can ignore it. But we're also going to add a path out to E as we do that. So we visit C. When we visit C, this less than or equal to becomes finalized. That is the best path to C. There may yet be a better path to B or D, and now we're adding one to E. So we look at every possible edge out of the node that we just visited C, add each of those to our list. If that gets us to a node that we have currently calculated a cost for, we're going to compare whether the new route to get to that path is better than the one that we've already calculated. If so, we'll make that change. We'll see that in a second. But we added C, we added all of C's connections, and we have now visited C. When we added E, we added the backtrack, the path that goes through C. So at this point, if we wanted to reproduce the path, We know that we can get to E with cost 12 at this point. The path that we use to calculate that would backtrack from E to C and backtrack from C to A. So that tells us the path is the exact opposite of that, A to C to E, to calculate the best path so far as to getting to that vertex. So the next question is, what is the minimum in this list of costs? That's the next thing we're going to do. Which one is it? B. We're going to visit B and lock in that too. We're also going to look at every neighbor of B and see that from B we can get to C. I already visited it. This path cannot possibly be better than the one that already exists. There's an outgoing edge to E with total cost be locked in 2 plus this 10, giving us 12. This 12 already exists, so you can bias this however you want. It's probably better not to update something once you've already found a path. But we'll also add an F at cost 4. So that's what we see when we update. The only change we made here, we visited B, locked in the 2, and we added F at cost 4. Which node comes next? Have a tie. We can break that tie arbitrarily because these costs are, both of these paths at this point are guaranteed to be optimal. The order in which we explore them does not matter. So we'll go to D next. When we expand D, we're going to lock in this 4. We're going to visit it, and we're going to look at all neighbors, outgoing edges of D. 1 goes back to C, but that's already been visited, so that path cannot be better than the one that we've calculated so far. And in fact, 4 plus 2 is in fact greater than 1. There's no reason to do that math. It's guaranteed to be longer because it's already, C was already visited. That's the only outgoing edge. So we will lock in the 4 for D and make no further changes to the table. We loop back around, minimum cost in this table of unvisited nodes, and we get F. So we're going to expand F. When we expand F, we're going to lock in this 4. And we're going to look at every outgoing edge from F. There's only 1. We're going to add H. And the total cost for that is the value that we locked in for F plus this cost. 4 plus 3 is going to be 7. So H is going to get a cost of 7. Looping back around, which one of these unvisited costs is smallest? 7. So we're going to expand H, which is going to add a path to G. So we're going to use the total cost of getting the H, which is going to get locked in at 7, plus the edge weight here 1. We're going to add a cost of less than or equal to 8 for G. Looping back around, which one is smallest? G. So we're going to take the less than or equal to 8 at that point, lock it in, find there's an outgoing edge back to F, that's already been visited, an outgoing edge to E. The total cost of G, 8, plus this 3 gives us 11, which is less than this 12. So we're going to update our cost here from less than or equal to 12 to less than or equal to 11, because we found a better path to E. It also changes the backtrace. So we were going through, we calculated this best path as 1 plus 11 as a backtrace to C, but now the best way to get the actual 11 here is to go back through G. So if we do that, there is one last node to expand this 11. We're going to just lock that in, visit it, and now we have a complete table of shortest paths as well as backtraces. So if we really wanted to find the path to get to E, how would we figure out the best path from A to E from this table?
E goes to G, E goes to H, H goes to F.
Yeah, so E to G, G goes back to H goes back to F goes back to B goes back to A. And if we do that in reverse, we find the A to B to F to H to G to E. That's the exact route that we took on the back trace, but in reverse. So that tells us that is the path that we want to take to produce that shortest path. questions on the process? Does that make sense? Does it make intuitive sense as to why this always produces the right answer? Anytime when you would query something that goes back to a visited vertex, it's guaranteed to be a worse path. And if there is a better path, it's only going to lead to an unvisited node. So we can in constant time query the best path that we found so far to this node, plus the edge weight to the new unvisited node. And we can now directly compare whether that is greater than or less than the existing path. If it's less than, we can update the best path that we've seen so far. And this eventually terminates with the best paths. Very elegant, yeah.
Is there a version of this that uses negative weights?
Yes, there is. As done before, and we'll talk about it once we're through a couple more examples. So in general, when we visit a vertex, the cost there is known. There's no way that it can be improved at that point. And we found following back pointers gets us there. While the vertex hasn't been visited, there may very well be another shorter path that we'll find later in a later iteration of this loop. But we can at least store the best that we found so far, and that helps us to eventually know once we visit it that that is the best path overall. So we did exactly this. We followed the back trace to get from A to E. We have a few more minutes, so what I'm going to do is let people get started on another example. So let's go ahead and take just a few minutes and fill this out.
Oh, yay. Well.
Vertices in a graph always store a reference to which of the edges leading to it has the lowest weight. If I'm interpreting what you're saying correctly, I think that that doesn't necessarily guarantee that that edge is part of a shortest path. What would that be doing for you? How would that be used or useful in your interpretation of the problem?
All right, come on. Come on.
In a case like this, we're trying to get from source to destination. If we're storing the incoming edge that has the least weight, there's no guarantee that that's part of the shortest path from source to destination. Am I understanding your question or misunderstanding that to some extent? Yeah, it's a good idea. Just happens to be that is not necessarily part of the correct answer. Not guaranteed. It frequently is. All right, well, we are just about out of time, so if you'd like to work on this between today and tomorrow. That way you can spend some time verifying at the start of class, we'll start to go over this. And work on the next couple of algorithms.
All right.
Well, I don't technically have office hours today. I will be in my office and can handle any questions. So I guess I technically have office hours. Swing by if I can be useful.
Chris, do you, I got a question.